Okay, so it looks like we're working on some double angle identities for trig, and you have these formulas that we have here that we're going to use as a resource in being able to verify some identities and eventually solve some equations. Sine of 2x is pretty straightforward. There's only one formula for it. It's 2 sine x cosine x. Cosine of 2x has these, I refer to them as three different flavors here. Cosine squared minus sine squared is kind of the fundamental one. And then you can also use 2 cosine squared minus 1 or 1 minus 2 sine squared. Just to give you a sense of how these could look, though, if they're a little bit more complicated, you might see something like the sine of, let's say, 10x. And what you would need to realize is that could be written as twice as much as the sine of 5x. So basically now this 5x here is kind of playing the role of this x here. This 2 is like that 2. So what you would see is this 2, you might think of it as coming out and moving to there, right there. And then what's you're taking the sine and cosine of is this thing right here, which is the x. Well, in this case, that is a 5x here and a 5x there. So you should be able to look at something like this and be able to go backwards and say, oh, I see that that's going to be the same as the sine of 10x. That's one of the ways these things can be just a little bit more complicated than just seeing, you know, a 2x in here and an x here and an x here. So here's an example that plays off of what we just looked at there with that brief example on the first slide. We're trying to show that this left side of this equation is equivalent to the right side. And what the rules are here is that we can make a replacement. We can substitute something with its equivalent, or we could factor a term, which again is kind of like replacing it with its equivalent. Think about something like it's okay to write 6 as 3 times 2. That 3 times 2 is the factored form of 6. And also you can do things like multiply something by a factor of 1, which would be maybe you want to multiply something by cosine of x over the cosine of x. Multiplying something by the cosine of x over the cosine of x is really just multiplying by 1, so it doesn't change the value, so it's legal, but that might help us get a common denom or something like that that could help you further on down the road. But anyway, for this first example, number 73, what I would like to do is work on this right side, because I see that we have 10x here, which is twice as much as 5x. So the first thing I would do is rewrite that right side as the cosine of twice as much as 5x. So clearly that's legal because 2 times 5x is the same as 10x. But then I can realize, hey, I've got a cosine of twice an angle identity. It says the cosine of twice an angle, I'm going to use theta here instead of x, is the cosine squared of that angle minus the sine squared of that angle. So in this case, if I just think of this as the cosine of 2 5x, that's the same as the cosine squared of 5x minus the sine squared of 5x. So I can go write that and say, oh, this is the cosine squared of 5x minus the sine squared of 5x. And then I look over to the left side, and that's exactly what I have there. And I say, okay, well, I've just proved your identity. Now, as I start this next example, number 75, you see this quantity here that's being squared, and we're trying to show that it's equal to 1 plus the sine of 2x. So the very, very fundamental thing you want to do in these problems is recognize on this side we've got the argument of the sine function. That means what you're taking the sine of is 2x. And over here, these are just regular x's. So something's got to change. Either we've got to turn this sine of 2x into something that just has regular x's, or we've got to work over here and maybe convert these guys into 2x's. So that's like the bottom line. There's only one way to do this, or well, I shouldn't say there's one way to do this. There's only one approach to this. You've got to turn regular x's into 2x's or 2x's into regular x's. So I think, I haven't done a lot of these. I think whenever you see a quantity squared in these problems, the best thing to do is just literally FOIL it out. So think of this as the sine of x, the sine of x plus the cosine of x multiplied by the sine of x plus the cosine of x. And then we're just literally going to FOIL that, and we're going to wind up getting sine squared of x. Now, when we do the outer terms, we're going to get sine cosine, and when we do the inner terms, we're going to get a sine cosine. So grouping those together, we would get 2 sine of x cosine of x's. And then when we do the last term, we're going to get a cosine squared, positive cosine squared. So the left side of this equation is exactly equivalent to what we started with. We just rewrote it as a product of two binomials, then we FOILed them out and we got this. And now we can recognize and say, well, hold on. This sine squared plus cosine squared, anytime you see sine squared plus cosine squared, that's always going to be equivalent to 1, provided that these arguments here, the thing that you're taking the sine and the cosine of, it are the same. So the sine squared of x plus the cosine squared of x is 1. If it was the sine squared of 10x plus the cosine squared of 10x, it would still be 1. It doesn't matter what the arguments are as long as they're the same. So that quantity there turns into a 1. Okay, but we still have this other stuff here, the plus 2 sine x cosine x. But I made a little cheat sheet down here with our identities for cosine of 2x, cosine of 2 theta, and the sine of twice an angle. And look at this, 2 sine x cosine x, 2 sine x cosine x. We can replace that with the sine of 2x, and that becomes the sine of 2x. The 1 goes along for the ride, and we look over here at the other side, we realize we have exactly the same thing, and we're finished. Okay, so here's one that's definitely going to be significantly more complicated. The last two examples we were really done in a couple of steps. First thing I would eyeball is we've got a 2x over here with a regular x with all cosines. Over here we've got all sines. We got a 4x and a 1x. So we have to kind of pick a side to attack. Now, depending on the teacher involved here, some teachers are very strict about saying that you can only work to kind of make substitutions on one side of the equal sign, and others are more lenient, say you can make substitutions here, you can make substitutions here, as long as at the finish line the two things are equivalent. Personally, that's my school of thought, because it doesn't violate the concept of what an identity is. But if your teacher is very strict about not doing things on both sides, it's always easy to kind of, once you can theoretically kind of make those two sides look like each other, you can kind of reverse the steps from one side and just make the other side longer. I kind of allow my students to do it one for one thing. It just makes the space a lot easier. Sometimes these things might take 7, 8, 10 steps, and it'll takes up half your notebook when you're doing it, so we don't want to have that situation. Anyway, let's see what we can do here. So my thought process on this is, because we've got a 4x here that's going to have to be reduced to like some 2x's, I think that's the place to go. Rather than trying to make the right side look like the left side, I'm going to choose to attack the left side and see what happens there. So my first thought is kind of like what we saw in that first problem. If you see a 4x here, I see that as 2 times 2x. So my first step is going to be rewrite that as the sine of twice as much as 2x, which we can rewrite as, when we see the sine of twice an angle, the sine of 2 times an angle, sine of 2 times an angle is 2 times the sine of the angle, cosine of the angle. So I can rewrite that as 2 times the sine of this angle, which is 2x, times the cosine of that angle, which is 2x. Oops. I forgot my sine of x that's in the denominator there. Let's make sure we don't lose him. Okay, so now we look at that left side and we say, okay, well, at least one thing you do is you start to say, okay, is this looking anything more like the right side? And I do see a cos 2x here and I see a cos 2x there, so that's kind of a good thing. What I think I want to do now is realize that this sine of 2x, maybe I'll highlight that in red, this sine of 2x that's right there, we can replace that with this guy and just kind of see what happens. So I'm going to write that numerator as 2 times, now that sine of 2x that's in red, I'm going to replace with this quantity that we see up here in the upper right-hand corner, 2 sine of x cosine of x, and then I'm going to go back to this black cosine of 2x that's right there, and put that all over the sine of x. And now I just realized we just kind of stumbled into a gold mine here. If we keep an eye on the right side and we say, hey, we need a 4. Well, I see a 2 times a 2, so that makes a 4. There is this entire numerator is all things that are being multiplied together. 2 times the sine times the cosine of 2x, all over a sine of x. Well, when you have multiplication involved and there's a common factor of sine of x in the numerator and sine of x in the denominator, we can take those two factors, sine of x, and cancel them out, which leaves us with this cosine of x that's in red, and that cosine of 2x that's in blue, and we look at the right side, and despite the fact that one of my cosines is in red, we've got exactly what we needed. So it looks like I made the right call on attacking this left side with that 4x and knocking it down to 2 times 2x, and then going from there, and it kind of stumbled right into it. And that's how most of these double angle identities work. Okay, I figured I'd jump down to 83. It's another one of the cosine and sine ones. I skipped a couple there that had tangents involved. One way to deal with those tangent problems, if you don't want to memorize the tangent double angle formula, is to turn everything into sines and cosines. Every tangent can be written as a sine over a cosine. They get a little cumbersome, but you can work with common denominators and make things happen. They get a little complicated, but it certainly can be done. Okay, so for this last one here, we've got cos to the fourth of x minus sine to the fourth of x is equal to cos 2x. You might think, okay, well, we got a cos 2x here and a regular x is here, so maybe we want to convert this into single x's. However, this cos to the fourth minus sine to the fourth, you have to start recognizing that at this point, after having an algebra 2, whatever, that when you see these even powers of something with subtraction in between, you got to go back to your original algebra of x squared minus y squared, that difference of squares pattern, which factors to x plus y and x minus y. So if you had x to the fourth minus y to the fourth, you'd have x squared minus y squared, x squared plus y squared. And you can see that as you FOIL these guys out, your inner and outer terms are going to cancel out, and you're going to wind up with x to the fourth minus y to the fourth. So if we kind of think about that, but instead of x's and y's, we think of cosines and sines, this thing will factor to cos squared of x minus sine squared, and then cos squared plus sine squared. And a couple things here. Whenever you're doing these problems, you kind of want to think, just in your head a little bit, okay, if I were to factor this, what would I get? And you'd think, okay, I got a difference of squares here, and I got this sum here, and then you start to think about what are those things? Well, cos squared minus sine squared, we love that. That is literally cos 2x, and so we can replace that with the cosine of 2x. Meanwhile, on this side, we have sine squared plus cosine squared, or cosine squared plus sine squared, which is our fundamental Pythagorean identity for trig that is equivalent to the number 1. So this this factor here becomes the number 1. That's a legal substitution. Wow, that's a really bad one. And this can be replaced with the cosine of 2x. So we wind up getting the cosine of 2x times 1, which of course is just the cosine of 2x, which is exactly what we were looking to get on the right side. So there's 3-4 examples worked out with these double angle things. Notice though, we relied on our algebra. We relied on the knowledge of all of those identities to kind of work with as tools. We didn't wind up using either of these two, but they can certainly come up in some of these problems. So you kind of want to have all those memorized in the back of your brain. But like I said, as far as these 3 flavors of cosine of 2x goes, this first one is really the fundamental one. That is the one I always recommend for my students to be kind of on the first option to go with. So hopefully that helps out on double angle identities.